All right, so we are going to move on to lesson 4.3, which is rotation. So let me present my screen and we'll get started. Okay. So rotation is another type of transformation, and it is another rigid motion or isometry because it doesn't change the shape or the size of the figure. So that means that distance is preserved, side lengths don't change, and angle measures are preserved as well. Rotation is a transformation in which a figure is turned about a fixed point called the center of rotation. Rays drawn from the center of rotation to a point and its image form an angle of rotation. So you can see in the diagram here, all right, we have this, I guess it's like a, I don't know what to call it, like a flag, I'll call it a flagpole with a flag, or you just think of it as a segment with a triangle on it. All right, so we have P is the center of rotation, and then this figure QR, the triangle, that is being rotated this direction, so it's rotating counterclockwise at an angle of 40 degrees. Okay, so they're showing the angle of rotation, and they're showing that the distance from the center of rotation to point Q is the same as the center of rotation to point Q prime. Okay, so the figure stays the same distance away from the center of rotation, and that's what all this says, what I just explained. Okay, if Q is not the center of rotation P, then PQ is equal to P prime Q. So again, just distance from Q to P and Q prime to P stays the same. And the measure of angle QPQ prime is equal to X degrees. Okay, that's just saying that the measure that is formed right here, this angle that's formed right here, that's going to equal whatever the angle of rotation is for the problem. All right. Coordinate rules. So these rules you are going to need to know. Okay, I'll just kind of circle them. And I do have a little trick to help you memorize these rules, but it's uses a Post-it note, so it's going to be a little bit harder to explain, not doing it in person, but I'll try my best. All right, so for a rotation of 90 degrees, and you can see here we're rotating counterclockwise. Counterclockwise rotations are positive, clockwise rotations are negative, kind of maybe opposite of what you would intuitively think. All right, but positive rotations go counterclockwise and negative rotations go clockwise. Okay. If we're rotating 90 degrees, and for this problem, we're just thinking about rotating this random point, which has a coordinate A, comma, B. Notice both are positive because you're in the first quadrant, positive A, positive B. All right, if we rotate it 90 degrees, well, because it lands in the second quadrant, it's going to have a negative X value, but it's actually going to be negative B, comma, A. So basically, the coordinate flips, and the B value had to become negative, the opposite, okay? Now, if we rotate it either 180 degrees, if you're thinking about rotating from the original, or you could think about rotating another 90 degrees, the rule is, if we rotate it 180 degrees, you're going to land in the third quadrant, which both coordinates should be negative, because if you start at the origin, you would be going left down. So it makes sense that they're both negative. From the original, the rule is that both coordinates just change signs. And then if we rotate from the original 270 degrees, that's going to land us in the fourth quadrant. The coordinates in the fourth quadrant, positive X value, negative Y value. If you're relating the new point, the image point, to the pre-image, the original, the rule is to change the sign of the A and flip it. Now, my Post-it note trick, I might just have to wait to show you in person in class, because I actually have to like turn the Post-it note. But what you can do is draw an XY axis on a Post-it note and just put like a smiley face in the first quadrant. I can't draw a smiley face. There we go. Smiley face in the first quadrant. This is your positive X. This is your positive Y. So right now the smiley face would have a coordinate of positive X, positive Y. Positive X, positive Y. Now, if I was to rotate that smiley face 90 degrees, okay, think about turning, this is why Post-it note would make more sense. If you turn your entire Post-it note over, what would this diagram, turn it 90 degrees, I should say, what would the Post-it note look like? So if I turned it 90 degrees, my smiley face would now be here. And if these labels stay where, or move with the Post-it note, I should say, if they move with the Post-it note, your X would then be up here and your Y would be down here. And you would think to yourself, to get to my smiley face, I have to move left and then up. And you're moving left along the Y and up, positive along the X. So it would be negative Y, comma, X to get to your smiley face. All right, well, that's the rule. Okay, we just kind of discovered the rule. The rule is to flip the coordinates and the second coordinate becomes negative. All right, if I wanted to rotate my positive, or excuse me, my smiley face into the third quadrant, 180 degrees, what would that look like? All right, so let me erase a little bit of what I have for a second. So if I was to rotate 180 degrees from the original, okay, so your smiley face is now in this quadrant. Again, the X and the Y have to move as well when you rotate. So if I rotate, the X was originally up here for 90, now it's over here, and the Y would come down here. So to get to my smiley face, I have to travel left on the X and down on the Y. So it's negative X, negative Y. Negative X, negative Y. That's the rule for rotating 180 degrees. And the last one of rotating 270 degrees. So if I was to rotate 270 degrees, my smiley face would now be in this quadrant here. All right, so again, the Y would, or I'll start with the X. The X would rotate here for 90, here for 180, down here for 270, and the Y would be there. So to get to my smiley face, I'd move right and then down. Right along the Y, down along the X. So positive Y, negative X. Positive Y, negative X. Okay. And then for 360, it just ends up where it was originally, so the coordinate doesn't change. All right, so if that little trick helped you, it's just a way to figure out the rule without memorizing it. I'll go over it again in person with an actual Post-it note so that you guys can see me actually turn my Post-it note, and then maybe it would make more sense, okay? That's just a little trick to help you memorize these rules, or so that you don't have to memorize the rules, I should say. All right, so it says rotating figure in a coordinate plane, graph quadrilateral RSTU, vertices R, S, T, and U are given, and then find the image after 270-degree rotation about the origin. All right. For those of you that are visual learners, you probably don't have a hard time with this. People who are not as visual, me being one of them, this is a little more challenging, and relying on the rules that I was just going over is going to help you. But some people can just kind of look and know exactly where this is going to rotate. I cannot. I have a more challenging time with this and need to rely on my rules. All right, so I'm plotting all the points. 2, -1. Okay, double check that I graphed that correctly. All right, so we have R, S, T, and U. I'm going to connect them to draw my figure. All right, I'm going to write those coordinates down here, R, S, T, and U. 3, 1, 5, 1, 5, -3, and 2, -1. -1. All right, so the rotation rule is that you're going to use a cursive R for rotation. You're going to rotate 270 degrees about the origin, so we use an O for the origin, points x comma y are going to map onto, so that's the original, that's the pre-image, are going to map onto y comma negative x. So again, you can use your post-it note trick to figure out that rule, or I'll just slide up. See up here, the rule's written as well. It says that you're going to change the x coordinate and flip them. Okay, so that means that r prime, s prime, t prime, and u prime. All right, if I change the x coordinate and flip it, it would be -3 comma 1. Change the x coordinate sign and flip it, it's going, oh, I wrote the last one wrong. I'm sorry, hold on. I didn't do what I said. Let's try that again. Change the x coordinate and flip it, I forgot to fit. 1 comma -3. Change the sign of the x and then flip it, 1 comma -5. Change the sign of the x and then flip it, -3 -5. And change the sign of the x and flip it, -1 -2. All right, so I'll plot those points. I have 1 -3. That's your r prime. Then 1 -5. That's your t prime, or s prime, sorry, 1 -5 s prime. Then -3 -5. I'm going to have to erase. Maybe I should label them over here. This is going to be t prime. This is going to be, oh no, that's s prime. Sorry. This is s prime. This is t prime. And then finally, -1 -2. And that's going to be u prime. Let me move where r is. Oh, darn. Okay, hold on a second. I have to start over with my labeling. So 1 -3. R here. R prime. 1 -5. S prime. -3 -5. It's t prime and -1 -2. That is u prime. Okay, so there is the rotation under 270. Now, how do I know it's a rotation of 270? How can I visualize it? If you connect u to the center of rotation and u prime to the center of rotation. So that would be this and this. All right, so from u, this is the pre-image, to u prime, does it look like it rotated 270 degrees? It does, okay? And you could do the same thing from R to R and R prime. Connect them to the center of rotation and see if it looks like a 270 rotation. Also, U and U prime should be the same distance away from the center of rotation, which they do appear today, okay? All right, let's keep on moving. Okay, the rotation postulate simply says a rotation is a rigid motion, which I already mentioned. Again, that means, what does it mean to be a rigid motion? It means that angle measure is preserved and distance is preserved. Okay, another way of thinking about it, the shape doesn't change size or shape. Okay, just changes location, position. Because a rotation is a rigid motion, the composition theorem guarantees that compositions of rotations and other rigid motions, such as translations and reflections, are rigid motions. So again, that just means that if you perform a rotation with a translation, or a rotation with a reflection, or a rotation, translation, and a reflection, because all three of them are rigid motions, your result is still going to be a rigid motion, right? You're still going to be left with a shape that's the same size, same shape as the original. It's just going to change location, but angle measure is preserved and distance is preserved, okay? So we're going to practice performing a composition. It says graph segment RS with endpoints R and S given, and its image after the composition, okay? So we have two different transformations to perform. All right, so we're going to graph R at 1, -3. This is R. And then we'll label S at 2, -6. This is S. We're going to connect them. There's segment RS. All right. And we first want to reflect it in the y-axis. So I'm going to write the coordinates down because I think it's good practice to think about the transformation, just thinking about the coordinates and not necessarily looking at the diagram. And again, because I'm not a huge visual learner, it's easier for me to just think about the rules instead of visualizing where it's going to end up, but you might have to visualize it, which is fine. All right, so if we reflect in the y-axis, you remember which coordinate changes signs? Think about it. Here's the y-axis. If I flip a point over the y, which coordinate's going to change sign? The x does. So R prime is going to be -1, -3. S prime is going to be -2, -6. The y-axis, this is your line of reflection right here. Try to go straight as I can. So if R is 1 unit to the right, R prime should be right here, which has a coordinate of -1, -3, which is what I wrote. Okay, S is 2 units to the right. So if I go 2 units to the left, here is S prime, which has a coordinate of -2, -6, which is what I wrote. Okay, the next transformation is a rotation 90 degrees. So we have to think about the rule for rotations. If you need to look above in your notes, you can, or think about the Post-it note. Think about turning that Post-it note so the smiley face is from the first quadrant to the second quadrant. What is happening? Okay, so the rule for rotation of 90 degrees, and I'll just write it up here. All right, you're going to have x comma y maps onto -y comma x. So you have to change the sign of your y and flip the coordinate. Okay, so changing the sign of your y and flipping your coordinate will be 3, -1. Changing the sign of the y and flipping the coordinate is going to be 6, -2. All right, so let's plot those points. 3, -1, and 6, -2. Here's S double prime, here's R double prime. Hope I didn't connect this segment. Ooh. All right, and again, if you think about the distance that R prime is from the origin and R double prime, all right, you can see that the rotation is 90 degrees about the origin. Okay. All right, just keep on moving along. Identifying rotational symmetry. A figure in the plane has rotational symmetry when the figure can be mapped onto itself by a rotation of 180 or less. That's hugely important. A lot of students miss this part. 180 or less about the center of the figure. This point is called the center of symmetry. Okay, so we have the line of symmetry when we're talking about reflections. We have the point of symmetry when we're talking about rotational symmetry. Okay, the rotation can be either clockwise or counterclockwise. The figure below has rotational symmetry about a rotation of either 90 degrees or 180 degrees. So think about this as like they're fan blades, right? If the fan blade rotates 45 degrees, oh, sorry, let me finish reading. Although a rotation of 45 does not. Okay, so if your rotation is 45 degrees, okay, does the result look exactly like the original? It doesn't. Okay, but if you rotate the fan blade 90 degrees, so this fan blade would come down here, this fan blade would go there, this fan blade would go there. All right, so this is a 90-degree rotation. Does that look the same as the original? Yes. So that means that this figure, this fan blade, has rotational symmetry of 90 degrees. Okay? If I rotate the fan blade, I'm going to start with this one, 180 degrees. Think about what that would look like. Would look like this. Does the original and the result look the same? So it has rotational symmetry of 180 degrees. Now, if I rotate it 270, it would again land on itself. So it does have a rotational symmetry of 270, but by definition, right, it says that a figure can be mapped onto itself by a rotation of 180 or less. So even though, yes, 270 degrees maps it onto itself, the figure would look the same, it's not considered rotational symmetry because it's above 180. Okay. All right, clear that. Okay, so identifying a rotational symmetry. Does the figure have rotational symmetry? If so, describe any rotations that map the figure onto itself. Okay, so the first is a parallelogram. Okay, I'll give you guys a minute to think about this. Do you think it has rotational symmetry? It does. Yes, it has rotational symmetry of 180 degrees. All right. And it's about the intersection of the diagonals. Okay, if I was to draw the diagonals of this figure, here's one diagonal. Here's the other diagonal. Ooh, try to get that. If I rotate about the intersection of the diagonal, so if this point rotates 180 degrees, okay, so this point here would land here, and this point here would land there. Would the figure still look exactly the same? So that's why it has a rotational symmetry of 180 degrees. What about the next figure? How many times can I turn it and it'll look exactly the same? How many degrees do I have to turn it to make it look exactly the same? So the answer here is yes, it has rotational symmetry, and it has rotational symmetry at 45 degrees, 90 degrees, 135 degrees, and 180 degrees. Because remember, your rotational symmetry is set to be 180 or less. All right, so if I rotate this point 45 degrees, it would map to there. If I rotate this point 90 degrees, it's going to map to there. If I rotate it 135 degrees, if I rotate this point 180 degrees, okay? So every time you turn it 45 degrees, the figure looks exactly the same, which is why it has rotational symmetry. Okay, and the last one, the trapezoid. Is there any way to turn it and make the figure still look exactly the same? Only way is if you rotate 360 degrees, which is above 180. So the answer is no, it does not have rotational symmetry. Okay. All right, guys, that I believe, let me just take a quick peek at what I have on the next page, make sure there's nothing I wanted to, nope, that is it for this lesson. So I will see you back here for the next one. Bye.